know where there's some. Right here in the hall clerk.
No, Molly, not in there. I have a
Hi, and welcome back. This is part 3 of the exploration of the Heathkit C-3 condenser checker. We restored it, cleaned it up, tried it out last episode, saw that it works just fine. And this time I want to explore how it works, what it does, how it does what it does. And so I started out, as I often do, with the schematic. And schematics with lots of switches confuse the issue for me. So what I usually do is, when I get confused, which is quite often, is I redrew the schematic into this one right here. This is actually what's going on inside the condenser checker when the selector is set from 0.001 to 0.5 microfarads for testing. This tube right here is the magic eye, and as we'll find out, the magic eye serves a way to measure voltage across a bridge circuit. So then I took this and simplified it further down into this one. This is what's going on as far as I can discern inside the tester. And I can tell you that when I first cracked this open, I wasn't sure what the 55 volt AC secondary winding on the power transformer was for. Turns out it's to run this bridge. This bridge provides 55 volts AC into the top and bottom of the 4 legs. They have a potentiometer here that's run to ground on its center tap, or its tap, and so we've got 10K across these 2 legs in essence. Across this leg we have a 0.02 fixed and known good capacitor, and then across this leg, that's where our test capacitor, the one we're testing out, goes right there. And then this circuit right here is the magic eye tube here. This 0.01 into a 10 megohm resistor gives us a balance, a measurement rather, across from the center tap to that point right there. And this is what is made up a bridge circuit. Here's a simplified, or very simplified version of a bridge circuit, and I'll demonstrate this in a minute. But what happens is you put a voltage across, in this case a perfect bridge with 4 10K resistors in that familiar diamond shape, and so you put a voltage across here, then you measure the voltage here. And in an ideal world, if all of these 10K resistors were exactly the same value, and I mean exactly, the voltage you get would be, well, there's a snap quiz. What would the voltage you expect here? If I put 12 volts DC across here, what do you think will be measured here? And that'll come to you in a minute, because I'm going to demonstrate what does happen. So here's a bridge circuit. It's 4 resistors. They're all 10K. What I'm going to do is take my old 12 volt power supply and hook the power supply right across here. Then I'm going to take the voltmeter and measure the voltage right across here. And you'll either be surprised or you'll say, well, of course, that's how it works. One or the other. So let's get started. Ooh, you got to turn this power strip on. Yeah, okay. So here's 12 volts. I'm going to go Let me put this on a piece of paper, easier to see. Maybe. Yeah, maybe. I'm going to put 12 volts positive down here, negative at the top. It really doesn't matter. It could go either way. And again, this is a DC voltage. And then I'm going to turn on the power supply. We now have 12 volts running in here across these two points on the diamond. What we're going to do is measure the voltage that comes out here. So first we'll confirm that we have 12 volts DC. Yeah, it looks like you can see that. .04. We have 12.04 is what's feeding into this bridge circuit. And across here is 12.4 millivolts. Yeah, millivolts. Minus 12.4 millivolts. If this had been a set of perfect resistors, this would actually be 0 volts. But a set of perfect resistors just doesn't, well, might exist somewhere, but I don't have them. These are 5%ers, so they're all out a little bit. And the result is that the measurement across the bridge is 12.5 millivolts. So that's what's happening with the bridge circuit inside the condenser checker. They're feeding, instead of DC volts, they're feeding 12 volts AC. And we'll look at that in a little more detail here in 1 second. So I clean all this up. The reason there's nearly 0 volts, in an ideal world there would be 0 volts across here, is because the amount of current flowing through this arm is exactly the same as this arm. If all of these components are exactly the same, then you get 0 volts. Now, an interesting thing about a bridge, or one of the useful things about a bridge, is you could, let's take this one right here. We could say we don't know what that is. So we could turn that into an unknown. We don't know what value that resistor is. Then if we turn this one into a variable, I'll just draw an arrow through it. Wiggly arrow, best I can do. Make this a variable. Then with the variable, we can change the amount of current that's flowing through this leg and this leg. So we can increase this one or decrease it, increase this one or decrease it. And at some point, we're going to hit, if this is within, some range of resistance, we're going to hit a point where we have nulled this out. This voltage across here will reach 0 or nearly 0. And when that happens, we know that mathematically, and we're not going to get into the math of this, but mathematically, the value we've found for this variable resistor plus these two 10Ks that exist in the circuit will let us calculate what the value of this unknown resistor is. If we're not on the mark, this voltage will go very positive. If you have a DC battery or a DC source like this, will go very positive or very negative, or not very, but it'll go positive or negative depending on which side of the null point you're on. What you're looking for is the null point itself, 0 volts across here. And once you've got that, you can then identify what the value of this missing component is, or unknown component. Now it turns out you can do this very same thing by using a couple of capacitors and a couple of resistors. You can test impedance. What you're measuring in this is impedance. With resistors, it's a direct resistance, but with capacitors and coils, it's impedance, and you only get impedance measurements particularly with capacitors, if there's an AC source. Recall that DC won't pass through a capacitor. It just builds up a charge on one side and then holds it there and doesn't let any more go through. So if you replaced this resistor with a known value capacitor and put an unknown value capacitor right there, same kind of setup. You can adjust the values of these two resistors, but now we've got, instead of DC, we've got an AC source. Then we can measure the impedance that the two capacitors are providing the circuit, along with the impedance / resistance of our two resistors. And that will again let us calculate what the impedance value of that is. And once you get that, then you can compare it to your known good capacitor that goes here, and you've got it figured out. Well, that's exactly what they do in the Heathkit. Let me pull this down a little bit more. They've got a 55 volt AC source going into a bridge. It looks very similar to this one, but you'll notice there's one difference in that they have a tap, the variable tap, the center tap on the potentiometer goes to ground. And they've got a 10K potentiometer here, so you can fish up and down and increase the current flowing through this way or through this way. And then they've got a known good capacitor. It's a 0.02 microfarad capacitor. In this case, if you were doing a different range setting, right now this is for 0.001 to 0.5 microfarad. If you were doing a different range setting, higher or lower, you would put a different capacitor in here, a known good capacitor value in here. Then you plug in your unknown one, and you measure the voltage between ground in this case and this side of the bridge. Now what this is doing, what this magic eye tube is doing, is that voltage, whatever voltage, whether it's increased or decreased, is driving the grid of this magic eye tube. And the way a magic eye tube works is if the grid has pretty much no voltage on it, there's a gap. That gap that you see, the dark band inside the magic eye, is because the cathode is allowing the grid bias, with the cathode pushing electrons toward the plates, is only lighting up one plate. As you increase the voltage on the grid, and again it's AC voltage, as you increase the voltage on the grid, it allows more electrons to hit the other plate, which brightens up that dark part, so that the electrons start to hit the dark part and fill it in, and this eye appears to close like that. So with this capacitor tester, condenser checker, what you want is for the eye to be wide open, which means there's virtually no voltage from here to here, across here. That means that in that case you've found the setting. You found the correct setting for the mystery capacitor right here. And that's exactly how this works. What else do I want to say about that? As I said, and if you're curious in bridge circuits, it's kind of interesting to paw through the literature, and there's a lot of it out there. Bridge circuits weren't invented in the 1800s. There's a lot out there, but you can do some really interesting measurement stuff using what is in essence a very simple circuit. If you have some known good parts, you can plug in unknown parts and discover what they are. So for example, we had this under test. This is 4.7 microfarad, 0.47 microfarad capacitor. So we had our test capacitor, a 4.7 microfarad capacitor in here. We knew we had a 0.02 in here, this fixed and then we'd adjusted this pot up and down to get 0 volts here so that the magic eye was all the way open. And if you look on the scale, let me get this kind of horsed around here. If you look on the scale, we ended up about here. See where that 5 is? That's the 0.5 microfarad range right there. We got, or 0.05, sorry, 0.5. It's right there. We got to almost 5, so 4.7. So we were on the right-hand side of the dial. If this pointer is pointing straight up, the wiper right here is smack in the middle of the potentiometer. So we got about, I don't know, a little less than a quarter of a turnover. So that means that we moved this thing a little, either a quarter that way or a quarter that way, in either case, to readjust the balance of the bridge so that would give us null voltage, 0 volts across here, which would then bias the grid on the magic eye tube to open the window, the little eye all the way. And that's, that's how it's working. It's fairly straightforward. Even if you could build the scale. If you knew if you had a bunch of capacitors, you knew the values, you could plug them in here and tweak this back and forth and find where on this scale, this scale right here, you could find out where those map out to and then extrapolate all the capacitance values if you wanted to. Or you could just buy a Heathkit C-3 condenser checker, your choice. One final example of what I'm talking about when I talk about the balanced bridge, and this is a real live example. I've got my voltmeter connected to chassis ground on the negative side, and the positive side is connected to the positive lead of the capacitor tester here. And I'm going to, right now you're seeing 136 millivolts, 139, around in there. It's varying around a bit. And the eye is open. Hope you can see that. Maybe if I cover that up. The eye is open. If I go to either side of that middle line, that voltage will go up. And that means the grid of the magic eye is now biased to allow all kinds of electrons to hit the rest of that plate and light up the rest of it so that the eye has closed entirely. If I go the other way, you'll see this drop, 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 drop down. The eye is opening now at about 0.085 volts. Eye is wide open, and then I'll go the other way, and the same thing happens. The AC voltage on that plate goes up and allows this to close. It's only at the point where the AC voltage on the plate, or the grid rather, is at its very lowest point that the magic eye opens up all the way. And that's null. That's a null measurement. That means that the bridge is perfectly balanced. Whatever resistance that this potentiometer that's in here has reached between ground on one side and ground on the other side is indicating what the capacitance of this capacitor is. So that's a final instruction on how this works. Now I wanted to make one other thing clear. I was talking about shut this off. I was talking about the non-polarized 2 microfarad capacitor that's under the chassis on this radio. And that's right here. And I said that Ben Anderson at B. Anderson TV channel said you could hook a couple of electrolytics together in series to recreate that. It turns out that I did a little more research, and that's true, but what I think I said in episode 2 was incorrect. I said hook negative to negative and positive to positive, and that's incorrect. No, I said hook negative to positive, and anyway, what you do is you hook both negative leads together, then the positive leads will act as these two leads here. So this trick with electrolytics to replace a non-polarized capacitor will work. The difference is that you have to divide the capacitance in half because you've got two capacitors in series. So we have a 10 microfarad here. If we hook two of these in series with the negative to negative and the two positives over here, we would have, in essence, a 5 microfarad capacitor. And I just don't know about the voltage rating on that. So a little more research is in order. If you do this, if you're thinking about doing this, check out his video. I'll try to find it and put a link below. And there's some great reading over in the, what's that site? Something to do with stereo, audio amplifiers. I'll try to put a link there too. Apparently it's a not uncommon practice for equalizers and such and the like. Okay, that's it for this episode. Thanks for watching. Hope you did. Take care and be safe out there. See ya.
The makers of Johnson's Wax.